Welcome back, and we're on page 10 of your notes and we're looking at cell diagrams. Now these are just a way of writing out what is going on in our two half cells, and it's just slightly easier to read. However, there are a couple of rules that you need to learn. So we use raw as a reminder of what's going on. So we take our reduced state of one electrode and turn it into the oxidized state, and then we take the oxidized state and we turn it into the reduced state. So in other words, it's a bit like reading a balanced stoichiometric equation. You read it in that direction. So in this case, if we look at what's happening, the zinc solid is being oxidized to zinc 2+, and the copper 2+ is being reduced to the copper. So we have our raw, our reduced state going to our oxidized state, and our oxidized state going to our reduced state. There are a couple more symbols you need to learn. This double line, sometimes you see it's dotted line, sometimes as a straight double line. This indicates the salt bridge. So this separates the anode from the cathode. Oxidation always occurs at the anode. The easiest way to remember this is that the valves go together, and reduction always occurs at the cathode. So again, the constants always go together. The other way of remembering this is red cat and an ox. So again, red, R-E-D, goes with the cat, and there is an A-N, ox. So that's another way of remembering it. So if the reagents are in the same phase, in other words, they're both solutions or both gases, then a comma is used to separate them. For some examples, we need a platinum electrode. If you remember back to our hydrogen electrode, this is simply a surface for the reaction to take place on. So for example here, we've got our platinum electrode. That always appears on the far outside of the cell diagram. That's just to show that we need it there. Then we have that in contact with my hydrogen gas. That hydrogen gas is separated. I've got a single line here. This represents a phase boundary with the hydrogen ions in solution. Again, notice it's the reduced state going to the oxidized state. I have my double line here indicating my salt bridge and indicating that these are my two separate half cells. And I've got my ROOR, my oxidized state going to my reduced state. Here, because these two species are in the same phase, they're separated by a comma, but they're separated from the platinum electrode. Remember, we need a surface on which this reaction takes place, with a straight line and the platinum on the outside. They do take a bit of practice getting used to these, and there are lots of different symbols you need to learn. Things like the double line mean the salt bridge, single line representing a phase boundary, a comma separating the two components. So let's look at a couple of examples. So here we have calcium being oxidized to calcium 2+, and iodine being reduced to iodide. So this is my oxidation reaction, and this is my reduction reaction. My oxidation reaction, my anode always goes first. So I don't need a platinum electrode in this case because the calcium solid can act as my electrode. So I have calcium solid is in a different phase from the calcium ions because these are aqueous. So I have a straight line, Ca2+ aqueous, double line to represent my salt bridge, and then I have my iodine changing into iodide. These are both in the same phase. Notice that there's aqueous here, so I've got I2 aqueous, comma 2I negative aqueous, and that will need a platinum electrode because there needs to be a surface on which that reaction takes place. So they're in a different phase. So I'm going to write and then PT on the outside. I can put these in square brackets to show that they are one system. The other thing you should notice is that this reads the same as the equation. So calcium to calcium 2+ here, and iodine to iodide, iodine to iodide. So let's do the next one. So you've got magnesium going to magnesium 2+, and zinc 2+ going to zinc. So this, again, this is my oxidation reaction, which occurs at the anode. So this one goes first. I don't need a electrode on this one, because the magnesium metal can act as my electrode, but it is in a different phase from the magnesium ions, and that is my reduced state going to my oxidized state, and then I have my oxidized going to my reduced. So I have zinc 2+, which is aqueous. Again, it's in a different phase from the zinc metal, and the zinc metal can again act as my electrode. The last one here, I have iron 2 being oxidized by manganate to iron 3. So this is my oxidation reaction, and it goes first. Notice we're going to lose the 6 in front of here because we're just doing the cell diagram. So I have Fe2, which is aqueous, going to Fe3, which is also aqueous. So I am going to need a platinum electrode, and they're in a different phase from the Fe2+ and the Fe3+. Notice the comma that separates those two because they are the two components. Again, double line to represent the salt bridge. Now we have the manganate, but the manganate won't work on its own. It does need these hydrogen ions. So I'm going to put these together. I've got MnO4-, and I've also got my 8H positives, and that makes one part of my cell which is separated, comma, from the other part of my cell, which is my Mn2+ and my 4H, just about fit that on, 2O, square brackets. The thing I've missed off and I've got room for is the straight line between that one and PT, because obviously it needs a platinum electrode for the surface on which this will take place. So that is E cells.